Okay, so a repeat, no need to on your camera, just listen to me. If you cannot see something, cannot hear something, you're supposed to be seeing the textbook right now. Okay, what is sound, right? If you cannot see that, right, if you cannot see the screen I'm talking about, please unmute yourself and let me know. Okay, before I start the lesson, I have a very interesting question from a student in this class. I suppose she's in the chat session somewhere. Right, the question is, if work done is a scalar, why is there such a thing as negative work done? If work done is derived from force, which is a vector, shouldn't it be a vector as well? All right, so I think it's a very good question, so I'm going to address it here. All right. Let me see if the student is in the class. Sure. Right, so anyway, it doesn't matter if she's in the class or not, it's a good question. I'll try to answer it. Okay, firstly, work done is a scalar, that is correct. Force is a vector, that's correct. So work done is given by force times, in your context, you study as force times distance traveled in the direction of the force. The truth is that actually that is a simplified version of what work done really is. All right, work done's actual definition is a mathematical function called dot product. All right, it's spelled DOT PRODUCT. All right, so what a dot product does is that it takes two vectors, which is force and displacement, right? And when you dot these two vectors together, it becomes a scalar, right? So the exact mechanics behind why that happens, you will learn when you go to JC, right? If you go to JC and study maths, you learn dot product, then you understand why a bit more that how two vectors can become a scalar, right? So the mathematical part, I'm going to not explain it, all right, because it's just going to take one whole lesson, all right? So that's not the point. What I am going to answer from this question is that, why is there such a thing as negative work done? Right. So I think one possible misconception you may have is that you've studied scalars and vectors and you realize that, hey, if I look at speed, speed is a scalar and there's no negative speed. If I look at vector like velocity have negative and positive. So in your mind, you may be thinking there's no such thing as a negative scalar, which would be wrong. There is such a thing as a negative scalar, all right? So what a negative scalar means is that it is how much in terms of magnitude below zero. Okay, so I'll give you a simple example. The best example for scalar I have normally is money. Right. So let's say person A and person B. One person has $5. The other person owes someone else $5. So person A would have $5 more than zero. Person B would have $5 less than zero. Right. If I contrast these to, let's say person A and person B are running in opposite directions, person A will have positive 5 meter per second velocity. Person B will have negative 5 meter per second velocity. However, their magnitude is the same. Okay, so I repeat that. So hopefully you understand. If I look at a scalar of +5 and a scalar of -5, right? The one who has a scalar of +5 means his magnitude is 5 more than 0. The one who has a scalar of -5 means that he has a magnitude of 5 less than 0. So a negative scalar means less than. Understand not? Contrast this with a vector like velocity. If I have +5 meter per second versus -5 meter per second, the magnitude is the same. Okay, because if I look at magnitude for +5 and -5, they are both 5, right? So I can say that these two people are running at the same speed. What does the negative in the vector imply? Opposite direction, that's all. Okay, so hopefully that clears up the ideas behind what's the difference between a vector negative and a scalar negative. Right? In the context of work done, when you have a negative work done, you must understand what positive work done means. Right? Positive work done means I pass energy from one body to another, or one system to another. Negative work done means the opposite. Right? I take energy from that system and redraw it. Okay, so that just means, and it's a magnitude change. All right, so it's nothing to do with direction. Okay, so with that, we'll start today's lesson. Okay, you should be looking at my textbook. All right, if you cannot see my textbook again, please let me know. All right, we should be on the page, what is sound? All right, and we're going to discuss the second part of waves. All right, you should remember that waves consist of both longitudinal and transverse types. The transverse we covered in quite a lot of detail, so I'm not going to bother anymore. Today we're going to cover the only longitudinal wave that is in your syllabus. All right. Okay. So anyway, so what is sound? Sound is a longitudinal wave, right, that can travel in air, right, created by a vibrating source, right? For all intents and purposes, sound can also travel in liquids and solids. In fact, it travels faster, right? We'll discuss a little bit more about that later, right? So you can look at what the textbook is saying. The sound can be a person's voice box. The source of the sound can be a person's voice box or loudspeaker, right? So in this context, right, a voice box is a loudspeaker for all intents and purposes is roughly the same. It's some sort of you can think of it like cloth-like material vibrating. And this cloth-like material, when it vibrates the air around it, all right, and that causes the sound to transmit itself. Okay, I'll show you examples of this in a moment. Don't worry so much. All right, so so its backward and forward vibration is passed on to the air particles. All right, so the cloth moves back and forth, which moves the air particles, and is similar to how the spring in this diagram works. All right, so I think most of you should have seen this video before. Okay, I'm showing a video from YouTube right now. If you cannot see a video from YouTube right now, please let me know. Okay, so this is a slinky. The hand in this case, right, is equivalent to the wave generator in your textbook. All right, so instead of wave generator, I have a hand, all right, because no tag. Okay, so off the sound. All right, so you can see that the wave generator, what it does is just move back and forth, right? This is the direction of vibration of the wave generator or the hand, right? And this is the direction of the wave, right? So you can see this part here, but you can see some reflection. Can you see that? When it hits this end, which is fixed, all right, it will come back, right? You can see that something comes back, right? It's just a bit weak, so it's difficult to see, right? We'll explore that a little bit more later. But this is the essence of what a longitudinal wave looks like. The direction of vibration is parallel to the direction of the wave. Okay, that's the key point to note about longitudinal wave. All right, so we are back to the textbook. All right, again, cannot see. Unmute and let me know. All right. If I look at sound wave, right? So I will see something like that, right? Hopefully you saw it in the YouTube video just now. If you cannot see, later on you just Google longitudinal wave slinky, and you can look at the sound wave slowly later, right? So you can see that this is the hand. Remember, wave generator is the hand. So that wave just moves left and right. Wave generator moves left and right. It produces something called compressions. Right? What are compressions? Compressions are, it looks like the particles are stuck together, not stuck together, but very close to one another. Right? And refractions is where the particles are far apart. Right? Can you see my mouse cursor, by the way? I hope you can. Okay, so and these are compressions as well, right? So this is what we call sound wave. Obviously, the compression is moving, okay? All right, so we'll move up to the next point. All right, here we have actual air, right? So just now we discussed a loudspeaker. How does a loudspeaker work? So a loudspeaker here, right, essentially also moves left, right? You can think of it like a piece of cloth here that is connected to some electrical circuit that can force it to move left and right. Right, so it's essentially like what the hand is in the previous case that on the video that we watched. So when this membrane, right, we call it membrane, so it's like something like a piece of cloth, okay, moves left and right, it will disturb the air, right? So originally the air particles is like that, right, in your textbook. They are equally distributed throughout the air, which sort of makes sense. You think about it, if there's some kind of air consolidated at one spot, I mean, they will sort of disperse, right? So they'll try to spread out. It's like not different from the idea where you go up a bus, you try and spread out, right? You don't go in like the whole bus is empty, but you choose to sit next to the one person on the bus who is seated, right? And then that's really weird. People feel you are like a bit queer, right? So you just spread out, okay? So you spread out as much as you can, right? So that each region here has roughly equal amount of air molecules. However, when a membrane actually vibrates, okay, it will actually disturb this equilibrium. This, maybe I shouldn't call this equilibrium, this kind of system whereby the air particles are sort of equally distributed. And what it does is that it pushes and disturbs the air, right? So that as the air moves left and right, because the membrane is disturbing it, it functions very similarly to the slinky that we saw just now. The slinky is just a spring, which is this one, right? So you will see compressions moving, right? Exactly like that, right? I'm back to the YouTube video. So we just show one more. Okay, you can see this thing moving, right? The air particles does the exact same thing, but every time a compression moves, a refraction moves after it, right? So there's always compression, refraction, compression, refraction. It's like something that exists. They have to exist together. Like you think about it, right? Because if some part compressed, the other part must be sort of sparsely populated with air particles, right? So this compression actually moves from left to right in this case, right? Similar to the compressions here in the wave generator and the slinky, right? Or the spring. The slinky is just a name for the spring, okay? Don't need to overthink it, right? So I'm going to show you how this air thing moves in this applet here. Actually, it's this applet. Okay, I'm on this applet, on this website, sorry, right? There's this very nice applet, right? And you can Google this. You can Google this. Let me just admit all the latecomers. All right, so you can Google this as sound animation longitudinal wave. That's what I Googled for. Then you search under images. All right, then you click this thing, something that looks like this. So this is like the membrane of the speaker, right? Or the skin, or the piece of cloth, if you will. Right. So what the membrane does is it move left and right, right? Then you see it disturbs the air particles, because it's pushing the air particles right. Then it comes back. The air particles will sort of like try to space out and move left, so to speak. So that creates some kind of motion like that. And you can see that this is a continuous motion. All right. Again, I say I'm looking at an applet. If you cannot see this applet, somebody needs to unmute and tell me you cannot see. Now, what I want you to pay attention to is the red dot here. Can you see a red dot here? Right. You look at this red dot. Can you see that as the compression moves from left to right? Right. This is the compression, by the way. Right. So this compression moves from left to right. The red dot moves from left to right, but then back to left. So what is this red dot doing? The red dot here is actually mimicking the exact motion of the piece of cloth here, or the loudspeaker. Right. So you can see this one. Actually, this one is a nicer video. Okay. Nicer. I don't know what it's called actually. This is a nice applet, I suppose. Yeah, nice image, mobile image, right? So this particle is actually moving left to right, and you can see the wave, right? So they contrast the wave below, and you can also see compression, refraction, and compression moving, right? So the compression, refraction, and compression will move along with the wave, right? But the particle can only move left and right. This should remind you of what a transverse wave is all about, right? A transverse wave is all about having a transverse wave is all about having the wave moving, but the particle being localized in a position. So the particle moves, but it cannot move with the wave, right? The wave is a propagation of energy, right? Not of particles, all right? True for both transverse and longitudinal waves, right? And of course, here you can see another type of longitudinal waves is actually the P waves in an earthquake. Right, this is something you learn in geography if you take geography. But in physics, the only longitudinal wave you need to know about is sound. Right? You don't need to know about earthquakes. All right. Back to the textbook. Yeah. So as I was saying, I hope you can visualize this better now. Again, if you cannot visualize this, please Google yourself sound animation longitudinal waves. Right? That's exactly what I Googled. Then click image. Right. So when you click image, you will find the website that I just showed you. Right. And then you just have to look at this for some time. Then you will understand what exactly the phenomenon is about. Right. Now we're going to do something a bit tougher. All right. What I need to do is get an A4 piece of paper, blank paper. It can be a rough paper, but the one side of the paper needs to be blank, totally blank. All right. And I'm going to show you how to draw out a longitudinal wave. All right, so wait, let me change my share screen now. Okay, I'm going to Microsoft Word. You should see something like that. All right, so if you look at this, you should see a Microsoft Word document with 10 or 11 blue dotted lines, and then some pretty ugly looking dots, all right, on the top. All right, so they're all black. Okay, I'm sorry, they're not very nice. Okay, essentially what this is trying to mimic is you need to understand what's going on here, right? So this A4 paper, I'd like you to split it up into something like, of course, use it in portrait mode, all right? Then I think I need minimum 10 lines, vertically downwards. Okay, dotted or not dotted, I don't really care. You can just decide. Roughly equal distance apart. What this is supposed to represent is when there is no sound wave, this is how the air molecules are roughly positioned. They are positioned equal distance apart. Right? This is no sound wave. Right? When the sound wave pass through, as you have seen at Hepler just now, right, there will be some kind of disturbance that shifts these air particles to different positions. All right. So I'm going to start with a simple one. Right. I'm going to start that this particle is at rest. Right. Later on, this maybe I'll draw this particle here. Okay, some distance away from equilibrium position. I'm going to call this A/2. Right. Why exactly A/2? I'll discuss later. Don't have to worry now. Then this particle, I will now draw here. Right. I'll call this A. Right. Then this particle, I'll draw here. Okay, I highly encourage you to draw along with me. Because if you don't draw along with me, later on when we solve more difficult questions, you're going to have a problem. Okay, so anyway, and then I'm going to draw rest. Okay, so what I've just tried to do here is, okay, let me try and point out to you where the particles are. Okay, hopefully you can see the particle is here. Here, right, this particle, okay, let me try and use red. This particle sort of new position is here. This particle new position is here. This particle's new position is here. And of course, this particle didn't move. This particle didn't move. Okay, the red pen you shouldn't draw. The red pen is just to illustrate to you, right? So this is the original state of the particles, right? And when a sound wave pass through, this is the new state of the particles. Right? Of course, I haven't drawn finish lah. If I carry on drawing, you should something like that. Okay, maybe I'll call this minus A/2. Right. I'll call this minus A. All this minus A/2. And again, rest. Okay. Now, again, this particle has moved to this position, and this position, and stay at rest. Okay. So what happens after this? All right, I'm going to just finish it. This particle will actually be, this particle is at rest, right? So you can see the particles at rest. I try to show you the particles at rest. This is rest. Right? This particle is at rest. Originally at rest, stays at rest. Okay, this particle is also at rest. Right, originally at rest, stays at rest. Right, this is in contrast with, for example, this particle, right, which originally at rest, but later on is not at rest. Can you see that? Right, so I look at the last one that is at rest, this one, right? So originally at rest, still at rest when the wave passed through. Okay, so I say again, this one is one time instant, this one is later on in time. The two rows are describing the exact same column of air, just that the first column got no wave passing through. The second column got wave passing through. Okay, so again, after I draw this, then you think about why exactly do I want to draw these things, right? So hopefully you can see something that after this point here, all right, the particle here, right, what would we expect it to do? Can you see that this point is the same as this point? Therefore, I will expect this point, I call this B to replicate what this point does. Right? So actually, it repeats itself something like that. And if I want to draw some more, it will be something like that. Okay? All right, so hopefully you understand what is going on. Right? Any questions so far before I move on? Because I'm going to move on to the graph of this thing, which is another big elephant in the room, right, that we need to address. But firstly, I need to check, do you follow what I'm saying so far? Right, anyone unpause, not unpause, unmute, maybe talk to me. Tell me if you're following so far, any questions? Yes, there are like 67 of you or something like that. Can anyone unmute yourself and ask a question or tell me you're fine, I can carry on.
Wait, Mr. Nang,
Yes.
since like the sound waves, I mean the speaker or like the sound wave starts from this side, why
Left-hand side, is it?
why are the particles at the start like at rest?
Good question. Let's have a look at the applet again. Right, so I'm at the applet now. If you look at, for example, this applet, right, that you see the red dot moving left and right. Right, if there had not been sound here, right, do you realize that this particle will be exactly at the center of where its motion is actually vibrating about, right? So that's when everybody is not disturbed by the sound and they are equal distance apart, right? So at any one point of time, right, what I draw is like a snapshot. That snapshot means that I take a picture of this wave, right? Unfortunately, this one, I don't think I can stop the wave, right? But if I take a picture of this wave, can you see that so many particles, surely some of them must be exactly at their rest position when I take that picture. Of course, if I take another picture, then that particle will no longer be at the rest position because the particle is continuously moving like the red dot in this applet. You understand what I'm trying to say? Somewhere along the train where the wave is actually passing through, right? Some particles must be at rest. Most particles will not be at rest. They'll be at some disturbed position away from the rest position, right? Which is exactly what are you all seeing the applet or the are you all seeing the applet? Or do I need to sharing? Yeah. See, this is why you all need to talk to me. You all are not talking to me. Okay, look at this red color dot here. Right, the red color dot is moving from left to right, right? But you realize that it's moving around a center position. Now, if I were to take a picture of this wave, that means I pause the wave. I cannot pause the wave, unfortunately, in this applet. But if let's say I pause the wave, or you take your handphone and take a photo of the wave, you realize that if I keep taking photos, right, at one point of time, this red particle must be at its rest position.
Mr.
Agree
we
or not?
cannot see the applet.
Oh, cannot see the applet still.
Yeah.
Okay, can you see the applet now?
Yeah.
Okay, yeah. So I was talking about this applet. All right. So again, we look at this red particle. It's moving left to right, left and right, right? But it's moving left and right in a manner that swings about its equilibrium position. Its equilibrium position means that it would have stayed there if there's no wave passing through, right? So the dotted lines that I drew in the previous Microsoft Word document, right? The dotted lines represent the equilibrium position. That means to say that if there were no wave passing through, all the particles will sit on that dotted line, equal distance apart. Okay, that makes sense, right? Now, if there was a wave passing through, what happens to the particle? Now I'm looking at just the particle, which means I'm looking at the red dot only. This red dot will move left and right about its equilibrium position. Very much like what a pendulum does, right? If you go and knock a pendulum, it moves left and right about the vertical that it starts in, right? The vertical that it starts in is the equilibrium position. That means to say that if nothing going to disturb the pendulum, it will sit there vertically. But if let's say I go and knock the pendulum, or I pull the pendulum up slightly and release it from rest, then it will swing, right? Then when it swings, if I take a photo of this pendulum many times, I keep taking photo, keep taking photo. Most of the time, the pendulum will not be at equilibrium position, but sometimes it will be, right? So the same idea applies to the Microsoft Word picture I'm trying to draw here, right? If you look at this, particle 1, right? I'll just name these particles so that it's easier to discuss. If I look at particle 1, right? At the next time instant, particle 1 is still at rest position, right? If I look at particle 2, right? Particle 2 now move here. If I look at particle 3, where's particle 3 now? Here. Right? If I look at particle 4, where's particle 4 now? Here. Can you see that most of the particles are not at its equilibrium position? Right? So if most of the particles are not at equilibrium position. It's similar to the pendulum case that we were discussing earlier, right? Because you can think of each of these particles as a pendulum. All right, so I try to draw another diagram for you. Hopefully you can see. Okay, so this is picture 1. Right, so this one picture. I can draw picture 2. Maybe later I take another picture. Right, then maybe in this picture 2, something like that will happen. Let me think. Yeah, so something like that. Right, so this picture 2, at some time later I take this picture, then you realize that, is this particle number 1 still at rest? No, particle 1, which is this particle over here, is now here. Can you see that? It moved to the right because the wave pushed it to the right. Right, and then you look at who's at rest now. It's particle 2, because particle 2 somehow went over here. Later on, it came back to this position to be at rest. Right. Actually, I shouldn't look at this. This is not the starting point. Okay. This is the rest position. Right. I shouldn't look at this one as a starting point. Right. So it'll be confusing if I look at it. I just look at picture 1 and picture 2. I just contrast picture 1 and picture 2. Picture 1, particle 1 is at rest position. Later on, it's not at rest position because it moved here. For B, right, just now it was somewhere here. It was somewhere here. Now it moved back to rest position. Right? For 3, just now it was here. Now it's moving back closer to its rest position, but it haven't reached its rest position yet. Right? Particle 4, right, is somewhere here. Right? Later on, it actually move more to the right. So actually, particle 4 move in this direction, right? Because it's moving more to the right. You can see that. Right? This is supposed to be A. Okay, this is supposed to be A over 2, A over 2. And all right, so again, you can see that if I compare picture 1 and picture 2, there's always somebody at rest. In picture 1, particle 1 is at rest. In picture 2, particle 2 is at rest because this is particle 2. All right? Can? All right. So hopefully that clears something up. Okay, I don't know what to do with this now. It's so untidy. Okay, yeah, I think I have to erase picture 2 otherwise you're gonna get very confused when I draw the graph later. Right? Now I just want to focus on the particles in picture 1. Right? So picture 1 is just, again, like you take your camera and you snap a shot of the applet that we were using just now. Right? So anyway, right. So here, now we want to think about how does this relate to the graphs that I learned. Okay, you remember that displacement distance graph for transverse wave is the actual wave when I take a photo of the wave. Okay, for sound wave, the displacement distance wave is not the actual wave because you know the actual wave looks like the applet, right? The applet I showed you just now is the actual wave, right? And therefore, right, when I look at a picture like that, for example, like this picture here, this is a picture 1 here is a representation of the actual wave at one point of time. And I'm going to try to express this in a graph. Right? How do I express this in a graph? I'll just try to draw my graph scale. Right? So I'm going to draw x-axis, y-axis, and x-axis here. Okay, something like that. All right. The reason why the equilibrium positions, the total lines behind are important, hopefully you understand now. Right? So you can see that if I look at particle 1, right, picture 1, and I compare it with its displacement from rest position, is 0 because it is at its rest position. Right? So if I look at particle 1, I'll mark the position of particle 1 here. If I look at particle 2, right, I'll realize that particle 2 moved A over 2 distance away from rest position because my rest position was the blue dotted line. I should sit on the blue dotted line if there were no waves. Right? So that's the meaning of the equilibrium position. And if I look at that, then particle 2 is some value here, which I'll call A over 2. Right? And I'll mark out particle 2's position here. I do the same for particle 3, right? I know particle 3 is at A away. A is short for amplitude, Okay, so you should know amplitude is the maximum displacement a particle can move from its rest position in a wave. Okay, so anyway, I'll carry on and I'll do particle 4. All right, why? Because it's again A over 2 away. Can you see that fully? Right, then I look at particle 5. Surprisingly, is at rest again, or maybe not surprisingly. Okay, then I look at this side. This will be 5, right? So let's just number the particles. It's particle 5, right? It's particle 6, particle 7, right? So if I look at particle 6, where is it? Right? You must realize that in this case, it moved left. Just now it moved right. If right is positive, what is left? Left must be negative, right? Because if I move right and that's taken to be positive, my positive convention is right, which means that any direction that moves, any particle that moves left must be taken as negative. And that's why this is a minus A over 2 value. Right, and of course I have A somewhere here. So the minus A over 2 value is here. If I check particle 7 is here. If I check particle 8 is here. Check particle 9 is here. And what do you have? You're supposed to have a nice sine graph, okay? And that means the shape should be quite nice. My drawing is imperfect, obviously, because I'm drawing on the computer screen. All right, so it should look something like that. And what about this part? You say, okay, so you can draw one sine graph for me. What happens after that? Right, you can just carry on. This is 9. Where's 9? 9 is the rest. I know this 10. Where's 10? 10 is technically A over 2, so 10 is here. Where's 11? 11 is A. So if I carry on drawing the graph, it will look something like that. You just carry on. But I realized that this is what? This is one nice distance called a wavelength. Right, so this is displacement and distance. Right, then the question will follow that this is a displacement distance graph of a longitudinal wave. Is this a longitudinal wave? Hopefully in your head you know that this is not the longitudinal wave. This is a representation of the longitudinal wave. All right, the longitudinal wave, if I take a picture, it actually looks like that, right? That's why I call this picture 1. All right, okay. All right, now let's focus on the next part of this thing that is difficult. Okay, you got to bear with me. I know the going is not easy. All right, but once you clear this part, this is the hardest part of waves. Then you're fine. Okay, if you look at a textbook, all right. Okay, let's just go back to your textbook. If you look at a textbook, all right, you realize that what I've covered so far is this part, right? So I've covered this part, right? And then I've covered displacement distance graph, right? What I have not covered is the pressure distance graph. All right, this pressure distance graph is new to you. You did not have this in transverse waves. However, for the case of longitudinal waves, you should realize that because of the way the particles are distributed, right? Versus its original setting, right? Originally, I'm uniformly distributed without a sound wave, right? Air is uniformly dense without sound wave, right? As per your textbook, right? But once I have vibrations from the speaker, there are compressions and refractions, right? So what are compressions? Compressions are regions of high pressure because the particles are all stuck together. Refractions are the counter to compressions, right? If you look at some particles, some area where particles are highly clustered, it must be the case that some other areas are very sparsely clustered, right? That means to say the particles from the R region, which is here, sort of move to the neighboring C regions, right? Some will move left, some will move right, depending on the particles, right? But in essence, the R region will be more or less empty, right? There will be particles there, just less, right? And of course, the compressions are regions where all the particles somehow cluster together, right? And this clustering moves with the wave, right? So the cluster carries energy and moves with the waves. Do not confuse this with the particles move with the wave. I kept showing you the red dot on the applet just now. The particles never move with the wave, all right? Just the same way as we discussed transverse waves, okay? Right, so anyway, back to my point, which was, if I look at this kind of system, right, and remember this is like a picture of the applet just now we saw, just that I just take one picture, and that's why it's stationary, right? So I can call C, right, this position C here, as the center of compression, right? So normally compressions are a region, they are not a position, right? So I'll say this is the compression region. This point over here is the center of the compression. The very same way I look at this part, I say that this is the refraction region. Some people call it rarefaction. I don't exactly know what the correct pronunciation is, but it doesn't matter when you write. You spell it the same way. Okay, so some people call rarefaction. Rarefaction, yeah, I just call it refraction. Okay, because I think it's just easier to say. All right, so anyway, the refraction region has a center as well. And this is what we call the center of refraction. Okay, and so on and so forth. All right, the center of compression corresponds with high pressure. Unsurprising, right? Because when your air particles cluster together, that's called high pressure, right? And the center of rarefaction is corresponding with low pressure, right? And what I need you to pay attention to in the pressure distance graph, very importantly, that this point over here, right, where the x-axis meets the y-axis, normally is 0. If you look at displacement distance graph, is 0. But for pressure distance graph, this point is not 0. This point is actually normal atmospheric pressure, or the pressure in the region if there were no sound waves. All right, or in other words, is this diagram over here. Air is uniformly dense without sound waves. If the air is distributed like that, the air pressure will be this horizontal line. Okay, therefore, if I cluster like that in the area of compression, I will have higher than atmospheric pressure. Likewise, if I sort of like spread away from the area like the center of refraction, I should be lower than atmospheric pressure. All right, Ken? And what's really interesting is that if you realize the center of compression, which corresponds to obviously high pressure, right, and the center of refraction, which corresponds to low pressure, are always at a particular position whereby the particle at the center of compression or center of refraction are actually particles that happen to be at their equilibrium position. Okay, so I'll try to say this again, right? If you realize the center of compression and the center of refraction, right, according to this graph, you can just follow the dotted line down. You realize that the center of compression corresponds to a particle at rest. The center of refraction also corresponds to a particle at rest, right? And this can be seen in the diagram that we just drew as well. If you go back to the Microsoft Word document, I'm back to the Microsoft Word document. Can you see that? If I want to look at this very complicated diagram, picture 1, and find the center of compression, which particle would I look like? Which particle would I look at? Right? I will look at the particles at rest. They are the suspects for center of compression and center of refraction. Because of what I just discussed, right? You realize that the high pressure point must be at rest. The particle itself must be at the rest position or the equilibrium position. So if I look at this particle over here, is this particle a center of compression or a center of refraction? I'll just look at the particles around it. So if I look at particle 1, this is possible center of compression or refraction. Then look at particle 2. Does particle 2 move away or towards me? Right? So particle 2's original position is here. Then I move away. Can you see that the particle 2 move here? So it move away. Particle 3 also move away. Then this point, which is position 1, must certainly be a center of refraction, right? Because it's low pressure. Everyone to my right move away from me. If I had drawn the left side, you would have seen that everyone to the left move away from me as well, right? Then I check the next one. So I already know the center of refraction, right? So yeah, just draw R here, okay? This is center of refraction, right? Then I check the next guy at rest, who is number 5. Then number 5, I look left, look right. I look left, I realize that particle 4 originally here, then become here. Then I look right, particle 6 originally here, become here. Am I being squeezed? Answer is yes. Everybody to my left is squeezing me. Everybody to my right is squeezing me. Therefore, this must be a center of compression. All right, and then so on and so forth. You look at particle 9, everybody to the left is moving away. Everybody to the right is moving away. This is center of refraction. Okay, so if I want to, I could carry on drawing, all right, for completeness sake, I'll draw the pressure distance graph. Right, so pressure distance graph, where's the center of refraction here? So this is low pressure. Remember that this is PATM, right? So, right, this is atmospheric pressure, right? So at this point, this is my center of refraction, which must mean that this is low pressure. So my graph is something like that. I know this is the lowest possible pressure, so I just mark out. I know this is low pressure. Then the center of compression must be high pressure, so I know this is high pressure. Right, then I know that again this is low pressure. How do I know this low center of refraction? Center of refraction is because of this particle one. I usually identify this is low pressure, high pressure, low pressure. Therefore, low pressure, high pressure, low pressure. Then I just fit the graph inside. And of course I can carry on. Once you're used to the graph, you sort of know how to draw it. Okay, so then this is exactly what is in your textbook, right? And I sort of drew it myself. And my take is that every time you do something, you must always be able to derive it from the fundamentals. The fundamentals is always the phenomenon. The phenomenon is what you observe in nature, which is precisely what this drawing is all about. Then you want to interpret it in a graph format, because sometimes it's easier to visualize it in a graph format, right? But you must be able to derive yourself. Because if you derive yourself, then you understand the full implications of what the graph actually means, which is the essence of what your education is really about, right? It's not about memorizing formulas, right? It's about being able to understand the links between abstractions like graphs and actual phenomena like what is being drawn in the diagram above. Now, is that an easy thing? The answer is no. But that's why people who can understand these things are valued in society, right? Because you can do things that other people cannot do, and these things are valuable. All right. So anyway, I think I will take a short break here. All right. So any questions so far? Questions? There are like 67 of you. I find it very unlikely that nobody has a question. The question, therefore, is who has the courage to ask a question? No? All right. So what I'm going to do is that I think I will stop lesson today. I don't want to press forward because I think today, if you can absorb what we have studied so far, is good enough. All right. So the rest of the time, I think we have something like 15 minutes left. All right. What I'll do is I'll end lesson, and then you can go off if you have no questions. If you are the shyer type and you want to ask a question when everybody has gone, okay, I'll stay until 10 o'clock to answer your question. Okay, your job today is just understand what we have discussed so far and finish textbook reading on sound. All right, so next 15 minutes is going to be a textbook on sound. All right, you should read until page, actually just finish until page 209. All right, so finish page 209. Okay, from 206 to 209, read yourself. All right, when the school opens and I see you in class, all right, first lesson, I'll ask you questions. Right, so with that, that's the end of lesson today. If you have no questions, you may go. Those who have questions, stay behind and ask. I'm stopping the recording now so that whatever questions you ask will not be recorded. Right, that's the end of lesson. All right, you may go.